In terms of these reactive forces, friction is probably the most difficult one to deal with. So friction is the force that tries to stop an object from moving. It has to do with surface roughness down here, in which at where two surfaces make contact. Now, in terms of the frictional force, most of you have encountered this. If you want to see a practical example, just slide something across your desk. It'll basically do the trick. But one of the difficulties with dealing with friction is actually, numerically dealing with it. The reason for this is friction is very inconsistently defined based on what it actually represents. If you were to take a look at this system at the microscopic level, so let's make a little zoom bubble here. What's happening here is there's roughness in the top surface and roughness in the bottom surface. And as you try to slide these surfaces past each other, they literally hit one another in a similar fashion to what you encounter in the normal force. Now, if they can't pass through each other, this normal force is actually going to try to stop them from moving past one another. Now, the reason why it's so difficult to deal with has to do with its quantification. For the frictional force, the only thing I can actually mathematically define for you is its maximum possible magnitude. Not its actual magnitude, not how much force it's actually applying in, not what direction it's in, none of that. I can only give you an upper limit for it. That upper limit is calculated by this coefficient of friction mu here, as well as the magnitude of the normal force. And the normal force, of course, is the one that is created by the object that we're trying to move, this box here, being unable to pass through whatever surface it's sitting on. Now, if that's the case, how do you deal with a frictional force? Well, the answer is very carefully. You have to actually look at what conditions your moving object is undergoing. Now, this maximum magnitude here you can calculate. You can find the normal force, you can find its magnitude, you can multiply it by the coefficient of friction, which depends on the roughness of the two surfaces in question. That by itself is not difficult. What is difficult, though, is actually using this to figure out how much frictional force actually gets applied. So we'll just leave this up in a box here for now, and we'll take a look at the different cases. So let's say you have a box, we'll look at it from the top down, that you're trying to move, and that will experience a frictional force. So what you need to do first of all is you need to ask yourself, is the box moving? Does it have a velocity? So let's say that the box does have a velocity and it's in a particular direction. So this red arrow here is the velocity of our box. If your box has a velocity, friction is actually not so bad to deal with. The frictional force will always be exactly opposite the direction that you're moving in, and it will always have its maximum magnitude. So this frictional force here will be equal to the coefficient times the magnitude of the normal force, and its direction will always be opposite velocity. So that by itself is not super terrible. So if you have a velocity and you're going left, the frictional force will be to the right. If you're going up, the frictional force will be down. It'll always be exactly opposite the direction you're going in. Because what the frictional force is trying to do is trying to stop you from moving. So if you're moving in one direction, it will always oppose you by going in the opposite direction. So that's case number one. All right, so this here is case one. And that's when you have a velocity. Now, if this is case one, then what's case two? Well, let's say we take all this away, and let's say that you have no velocity. So the question is, how do we deal with this? Well, what you have to look at when you have no velocity is the direction of the applied force. So let's say that you are pushing this thing this way. So this is the direction of your applied force, which we'll call F applied. So the question is, if the surface is underneath you here, how do you determine your frictional force? Well, it depends on how big the applied force is. If you have no velocity, your frictional force, number one, will always be opposite the direction of the net force, or the applied force in this case. Right, so if you're pushing this thing to the right, the frictional force will be to the left. Right, so this applied force, we're probably better off saying the net force. Right, so this frictional force, the direction of it is opposite the net force. Now, the reason this becomes tricky is, although this seems easy enough, let's just bold my vectors properly, this only refers to the direction. Right, so it's opposite to the net force in direction. Right? And the reason I make this distinction is we now have to compare the magnitude of the net force to the frictional force. Friction will only oppose the net force up until it reaches either its maximum magnitude or it cancels out the net force entirely. So, specifically speaking, if you want some concrete rules for this, what you then have to do in case 2 here, when there's no initial velocity, is you need to compare them. If the frictional force, or the magnitude of it, is greater than the net force, so if the maximum magnitude of the frictional force is greater than the magnitude of the net force, one second here, I just want to get this set up properly. What you will actually see is the frictional force will only exert enough force to cancel out the net force. In other words, if the maximum allowable magnitude of the frictional force is bigger than the net force, the frictional force will cancel out the net force that you had previously. And what this will do is it will always yield you an overall net force when you add it in of 0. In other words, if the frictional force is bigger than the net force, it'll just cancel it out and give you 0. It won't apply itself up to its maximum magnitude. It will only apply enough to cancel out your net force. Now, the other case is if the frictional force, or the maximum magnitude of the frictional force, is smaller than our original net force for all the other forces present. In this case, the frictional force will simply apply its maximum possible magnitude. All right, so case 2 is actually the case that's hard. So just to summarize, if you have a velocity, the frictional force will be its maximum amount in the opposite direction that you're going in, all the time, 100% of the time. If you have no velocity, though, you have to actually compare the applied forces, or the net of all the other forces that aren't friction, to friction. If the maximum magnitude of the force of friction is bigger than all the other forces added together, friction will only apply itself enough to cancel out all the other forces, which will leave you with a net overall force of 0. In other words, if friction is bigger than all your other forces, you're not going anywhere. Now, if the maximum magnitude of the force of friction is smaller than all the other forces put together, so smaller than the applied net force, friction will apply its maximum possible magnitude in the opposite direction of all the other forces added together to try to slow it down. Now, that's relatively confusing. That's why friction is a reactive force, and why it's so confusing. Typically speaking, it's going to change its behavior depending on what you're doing. But these two cases cover all the instances in which you have to deal with friction. So when you're dealing with something like friction, you need to know what your system is doing to determine the direction of the force of friction, as well as how much of its maximum possible magnitude it will actually bother applying to try to slow you down and get you to stop. Because friction's ultimate goal is to prevent you from moving.